All right, so continuing with the next section of chapter 12, the chapter on round things, we're going to talk about the Galilean moons of Jupiter as a special case of some pretty large and interesting moons. These four moons are rightfully associated with each other because they are the biggest moons of Jupiter by far. They also have a historical significance which is implied by the name, and that is the fact that they were seen by Galileo, documented by him. They were the first moons other than our own that were ever seen in the solar system, so they have a real historical significance, as well as not, it's like it's an exhaustive list, right? There's not other large moons of Jupiter. These are the four large moons of Jupiter. Galileo didn't miss any, in other words. It so happens that it is kind of easy to see all four, although Callisto is harder to see. And depending on where they are in their orbits, they're not all visible at the same time. But if you look through what we consider today, a basic telescope, which of course would have been cutting edge back in the late 1400s, you would see four little dots under ideal conditions, which are clearly in a line because they have their own orbital plane around Jupiter and all around one much larger glowing sphere, which is Jupiter itself. And so you can really, with a basic telescope or a good pair of binoculars, really see these moons. So what are their names and what do we want to know about them? So in order of closeness to the planet, so in order of orbital radius, the names are Io, Europa, Ganymede, and Callisto. We see images of them, zoomed in surface images as well, both in color and black and white. The black and white kind of highlights different features like contrast, right? Maybe to see elevation more clearly. The surfaces do seem to be pretty dynamic, right? There's not one thing we could say about all of them, and we'll certainly get into what's going on with, Io's surface, Europa's, and then in contrast, Ganymede and Callisto, which have more in common with each other. So the evidence that Jupiter's large moons likely formed by accretion, remember that's the smashing together of matter, in a disk of materials surrounding Jupiter are what? Look at your options here. All have circular orbits, orbit in the equatorial plane, revolve in the same direction, have densities, which degrees of distance. So what do you think? Check in the chat. So I got to revolve in the same direction for a couple of you. That's a good guess. So you're not wrong, those of you that said 3. It's just not the whole story. Yeah. Yep. Peoria, yep. And yes, 2 and 3. Exactly. The circular orbits don't tell us necessarily. There's a thing with the values of their orbital periods. But if anything, that actually leads to a little bit of like distortion to their circle. And the circle itself is not strong enough evidence of, accretion moon as opposed to captured moon, right? That's going to be kind of our main different classifications. Captured meaning that the moon got created somewhere else in the solar system and then just got pulled in by the planet's gravity. And in that case, you wouldn't necessarily have, same direction or that clear planar orbit. And it's like I mentioned, the straight line, they really form a straight line of dots, like it's really visibly obvious. Yep. So yeah, 2 and 3, I absolutely agree. So yep. And by the way, one that is totally like a wrong answer would be 4, because the density is decreasing with distance just isn't a thing. There, and this is, I just want to point this out because it's so easy to make this logical mistake. With differentiation, we talk about, and this is like planets, right? When planets form, and they're still liquid, the denser material sinks to the core. It happens with the Jovian worlds and the terrestrial worlds. So, okay, denser things sink. That also matches our everyday experience. With orbits, there's no such equivalent. Denser material doesn't orbit closer to, the sun or the planet. They're not related. Density is not related to orbital distance. The terrestrial planets aren't denser because they're closer to the sun. Instead, because they formed closer to the sun, they ended up being denser because they couldn't hold on to gas. So, but it's not like the denser material sunk towards the sun in an orbital sense. It just doesn't work that way. I mean, if we go back to what were the physics behind orbits, we can easily show it, but we won't in the interest of time. But trust me that they're totally separate. No relationship between density and orbital distance. All right. I'll switch over. I'll mention this one, but I won't check answers. Which answers are evidence that Jupiter's large moons likely formed by accretion? Let's see. Okay, so we saw that one. Huh, I think it's a typo then. All right, an unfinished question by the looks of it. So these are like little planets, right? I mean, we have Ganymede and Callisto. I remember because I was shocked by that because I'd always thought, sorry to jump back, but I'd always thought that the only one that was bigger, no, it's Titan. Okay, yeah. So of the Galilean moons, Ganymede is the only one bigger than a planet. But still, with one of the moons being Ganymede, being bigger than a planet, it is kind of like a little solar system, right? It's a moon system, right? It's quite a gravitational, dynamic situation. All of these large moons, as their shape implies, are differentiated. They absolutely have rocky mantles, metal cores. At least they have cores. So it is worth pointing out that they don't all have, okay, so they all have cores and they all have differentiation. That's true. But I did stumble my words to say that they all have rocky mantles because they don't. Some of them actually have these large subsurface oceans, almost like a mantle of liquid water. Okay, so Europa has this whole ring of liquid water that sits between a very thin surface and a rocky mantle. So the rocky mantle is the orange color, and then that ring of blue is the subsurface moon-spanning ocean of Europa. Okay, and this is water in the H2O sense. This is liquid water. Ganymede has icy upper and rocky lower mantle. So Ganymede, it has a consistency and a differentiation that is more common and that I've talked about in various points. So I don't want to repeat myself too much, but when I talked about Pluto and I talked about Kuiper Belt objects, the KPOs, and how they're all made of this like mixture of ice, right? Well, like here they're summarizing and saying that the upper layer, the really like kind of the mantle, the upper mantle is ice. It's not all ice. It's a mix of ice and rock, but it's a lot of ice. And that's really common in the outer solar system. A lot of the moons have this composition. Certainly dwarf planets have this composition where they're largely made of ice. But on a big scale, Ganymede is a huge world, right? It's bigger than Mercury. It's thousands of kilometers thick. So this is would put like an ice sheet, a polar cap, let alone a glacier to shame. This is a lot of ice. Callisto, it's interesting they put it as undifferentiated. I haven't heard that before. it certainly seems to contradict the idea of it being perfectly round. I guess it could be an exception to the rule that you have a round world that is undifferentiated, but I don't know if that's completely agreed upon. So wouldn't hold you accountable for that. Generally, we don't talk about Callisto that much. And any facts about Callisto are just going to be, it's there, it's one of the four moons, it's the furthest one out, nothing about its interior. So I've never asked anything about its interior, which I guess is part of the reason, that I'm surprised to hear this. And also, it does seem counterintuitive. About to say that counterintuitive things do pop up, right? But this one, I don't know. So in terms of their distances, right, and one thing that you would want to know about all four of them, including mysterious Callisto, is going to be how far away they are from Jupiter. The units here, not kilometers or anything, but radii of Jupiter. So kind of a nice to visualize because you think about, how far this moon is. You can kind of think about its scale relative to the size of the planet. And Io is really close, right? So it's only 5.9 radii away, so it's less than 6. Compare that to our moon. Our moon is 60 Earth radii above the surface, so 10 times as far, relative to our planetary size. So imagine if our moon was only 6 Earth radii away. It'd be huge in the sky. It'd create incredible tides, so that this is a real close moon. Of course, Io is much smaller, right? And that's actually going to be also a trend that we see with the Jovian moons, is that they absolutely can be very close to the moons, can be really close to the planets. And it's because they're so much smaller than the planets, it's possible for them to have these stable orbits that don't just decay into further orbits. Because if you put the moon that close to Earth, the tidal friction would be so great that it would cause a loss of the energy that sustains orbit, and that would cause the moon to drift away. And by the way, that's generally what happens. Moons, you don't generally lose energy and causes them to spiral inwards. Losing energy usually means going to a stable orbit that matches that slower velocity, which is actually further away. And that's been happening with our moon for hundreds of millions of years, billions of years. But I don't want to rehash all of that. We talked about it briefly before. But anyway, moving on with Europa. Europa is just under 10 away, right? It's about double the distance. And then and almost another even step, we have Ganymede. And then quite a bit further out is Callisto. So Callisto is on its own, much further. So these three moons, Io, Europa, and Ganymede, are discussed together because they actually do share some behavior gravitationally, physically, and then Callisto is not involved. Okay, and the number actually, the orbital period is what they share, and I'll mention it again in a second. But these numbers and the fractions that get formed from the different values of their orbital period tells us an interesting story. Densities real fast. We have fairly dense Io and Europa. That's because they've got those rocky mantles. The rocky mantle not existing for Ganymede. Ganymede having a much greater proportion of ice means it's much less dense. And so this density, again, pretty similar to Pluto, right? So this is what I've heard described, like, worlds like this: Ganymede, Triton, Pluto, Eris, Makemake, so really any of the Kuiper Belt dwarf planets, they're all essentially oversized comets. They have a really similar, they're denser than a typical comet, but they have so much ice that they're more similar to a comet than anything else. They're big ice worlds. So remember the numbers: 1.77, 3.55, 7.15. Said we come back to it. Well, it's because of this idea of orbital resonance. So these three moons have ended up in a state, which is just like a natural physical state to arrive at, where their orbits are related to each other. And this allows them to sync up in a certain pattern. So what happens is, as a consequence of orbital resonance, is that the occasional tugs pull the moons into slightly elliptical orbits at conjunctions marked by flashes, gray, green, or magenta in the animation. So I could open it up for you, but in the interest of time, you can go to it yourself with the link. Galilean Moon Laplace Resonance Animation 2. Quite a name, right? But there's lots of good animations online that show the resonance of these three moons. You could just Google it and find lots of videos that display it quite nicely. And what I will just describe is that for every orbit of Io, so notice Io is written as 1:1. That's like a ratio, and it just kind of sets the stage, right? Because it doesn't really tell us much. But when you get to Europa, it says 2:1. Well, that means that Europa completes an orbit in half the time of Io, or Io completes 2 orbits for every 1 Europa orbit. So it's not, some weird fraction, right? It's not like, Io completes 3.3 orbits for every 2 Europa orbits. No, it's exactly 2:1. They're pretty darn close to exact. So that means that every 2 Io orbits and every 1 Europa orbit, the planets line up. And they make what's called conjunction. Conjunction is when they form a line with the orbital body. So if we were in conjunction of Mars, it would be, directly away from us relative to the sun. So like pointing directly away from the sun. And if we're in conjunction of Venus, it would be pointing directly, us and Venus would be pointing directly towards the sun. Ganymede is part of that too, because it completes 1 orbit for every 4 Io orbits, which means every 2, right? Because 4 divided by 2 is 2, every 2 Europa orbits. So there, right? Every time Ganymede comes around, it's going to line up with Europa and Io, and Europa will have gone around twice. One time that it goes around, it didn't line up with Ganymede, but every second time it will, and every 4th orbit of Io will line up with Ganymede, as opposed to every second orbit lining up with Europa. So they're just really regularly coming into conjunction, and so that causes them to get tugged towards each other because of gravitational attraction, and it's created this. It's just this state. It's kind of like if you've ever seen the like these videos that show and demonstrations that show like a room full of, say, like pendulum clocks or metronomes, and they all start out of sync, and then after a while they all get synchronized. So it's because of all the small interactions between them, right? They're all in the same room. The air, they all share the same air. The vibrations travel through the floor, and that causes this gradual state of resonance. And so resonance can take that form of all just being exactly in sync, or it can take a form of sort of a pattern that is synchronized but not identical. And here they couldn't be, because they can't have the same orbital period and be different orbital distances, but they can end up in these even multiples of each other. And it's just a natural state to end up in when there's strong forces that allow them to interact with each other, which was the case, because they're all close. They're all quite close to each other. And just to kind of like hopefully not over explain it, but the reason that they can be so close to each other is because they're orbiting such a relatively large mass, and it's not like the sun where you can't orbit that close under the conditions of the sun. It just puts out too much energy, so it's not a stable place for any planet to be. In other words, Mercury is about as close as a stable planetary orbit can be, and not get destroyed by the outcoming energy of the sun, including getting engulfed in a bunch of like big kind of like solar flares. So, but Jupiter doesn't have that. These orbits are totally sustainable, really close in. And so that, so these 4 moons can exist quite close to each other because of that dominating force of the moon, but that doesn't mean they can interact, hence resonance. But it's just sure a neat thing though, right? Just that you see these like patterns pop up in nature, right? And people talk about patterns in flowers and the biological world, and we see them in the physical world too. So quick summary of facts about Io, and then we'll probably do this for the next couple ones and take a break in around 5 minutes, our halftime break. So mostly rock, as we said, fairly dense. right? Quite dense for a moon, right? Because generally moons are less dense, because mostly further out in the solar system have a lot of ice. It does have a very thin atmosphere. Sometimes Titan, which we'll talk about, which is the moon of Saturn, is described as the only moon with an atmosphere. That's not strictly true, since Io does have a thin atmosphere, but it's quite thin. Okay. It basically is created by ongoing volcanic activity. So if you're in that kind of falls in that gray area, do you call it an atmosphere? We actually ran into the same issue when we talked about Mercury, because Mercury, yeah, sure, it's got this atmosphere, but it's not about gas retention. It's about continually, vaporizing the dust on the surface because the incoming sunlight, X-rays and other, ultraviolet and so on, as well as the solar wind, electrons. And so you've got that, continual vaporization, and so you're always producing a little bit of vapor, and it holds onto the planet. But it's not about being retained. It's not like a stage of an atmosphere, as we always talked about, the primary, secondary current, or in the case of the Jovian planets, the primary that just stuck around until today. So it's like, do you call that an atmosphere or not? Because if Io's volcanic activity ever stopped, then it would just lose its sulfur dioxide thin atmosphere. But perhaps more importantly is that Io is famous for its volcanism. It is by far the most volcanic body in the solar system. Not just the most volcanically active moon, but just body. There's no, even Earth doesn't have as many volcanoes, especially per area, as Io does. So why is that? How the heck can a moon be so volcanically active? Because conventional logic tells it might not be. Small bodies should cool. This thing was made 4 billion years ago. All the energy should have just escaped into space. That shouldn't have a molten core anymore, but yet it does. And that's because of tidal heating. The fact that it's orbiting this gas giant at such a close orbit means that the tidal forces are sufficient to actually rub rock together, create enough friction to melt rock. So, we talk about tidal forces causing tides, right? But do the tidal forces that Earth exerts on the moon do anything to the moon? Not really. They did in the past, which is why the Maria are only on one side, the side that faces us in the tidally locked orbit. But currently, no, because they're not enough to now melt the rock that is completely cooled, which forms the moon. Well, Jupiter's tidal forces are way stronger. It's a much larger planet. When you actually calculate the values, they're totally sufficient to actually melt the rock, and that's what happens, and it just sustains the volcanism. All right, and where's it coming from? Outgassing. I just give you the answer here. Just to continue outgassing of the volcanoes. Sulfur dioxide is widely associated with volcanic activity. We kind of mentioned that, but just to make it clear. So both carbon dioxide and sulfur dioxide are outgassed by molten rock. Io's atmosphere only has the sulfur dioxide in it. Which gas is heavier? Well, all right. This is a good. I want to make sure, see if you get this one. So I'm gonna check the chat. Let me get your answers. Oh, and it's fine. I'll just ignore your second submission, Elena. So as long as you did it the first time, you're good. I saw it in chat. Sorry, and I missed the stuff when you first posted, because I hide the chat for a while. All right, cool. Thanks for answering, Alexander. Is asking which gas is heavier based on this information. The fact that the carbon dioxide is escaping right into space. How I said the volcanism, if the volcanism stopped, the sulfur dioxide would escape. It would take a while, but it would eventually. All right, so everyone says sulfur dioxide must be heavier, and you are right. It's that whole idea that the heavier gases are the ones that are easier to retain. Carbon dioxide is quite a bit lighter, made out of heavier or lighter elements, just carbon and oxygen, as opposed to sulfur and oxygen. And sulfur is, maybe it's like, I don't know. I don't remember its atomic number. I'm bad about not having the periodic table memorized. So Maybe you have it memorized. Cool. Volcanic eruptions. Here's an image of one, right? And we can see like some time photos taken months apart, April of 97, September of 97, July of 99, and you can see what happened in terms of this the ash settling and the changes in the surface. So there's just if you're someone that wants to study the surface of Io, you'd have a lot of data to keep up with. It is constantly changing. So tidal heating, what's going on? It gets stretched out, right? At perihelion, right? There's the stretch is getting dramatized, right? As it gets closer, it gets even more stretched. Look at that. Becomes like a football. And then the stretching recedes. So that constant flexing, right? So yeah, it's a little silly because it's over exaggerated, but I think it does visually display what I was, describing. The planet is flexing and all that energy has to go somewhere. All that heat ends up melting rock, right? Keeping the interior warm. Otherwise, it'd just be totally cool, like our own moon, right? All the heat would have escaped into space. So that's the tidal heating, right? And remember that resonance? Well, that resonance, first of all, contributed to the elliptical nature of the orbit. And then on top of that, there's the poles. Every four orbits, it's lined up with Ganymede, which is, particularly big. And every second orbit is lined up with Europa. And so it's getting pulled even more. So the fact that it's so volcanically active is no surprise in a sense, once you consider all the strain it's under. But it is noteworthy that it's rocky and yet being tidally heated, because we'll see with every other case where we talk about a quote unquote surprising amount, although I suppose it becomes less surprising as you see the pattern, but a surprising if you only knew about the moon, right? The Earth's moon, and said, oh, hey, things that size have to be completely cool. Well, not the case when you go out to these, Jovian worlds and their moon systems, almost call them planetary systems. But the point is that when I talk about extra heat for all these other moons, they're always going to be fairly icy. And part of the argument is that, well, the ice has a lower melting point, and that's why it's even easier to keep them, active, keep, basically liquid, in this case, largely liquid ice underneath the surface. But that still can drive not like volcanism like on Io, but lots of behavior, right? There are such things as ice volcanoes. Pluto has them. So does Triton, in fact, which is a moon of Neptune. And so you have this type of behavior, and it's probably going to happen with that lower melting point worlds like Ganymede. Although Ganymede, it as a kind of counterexample, doesn't have a lot of activity. But then again, it's the furthest one out, right? So it's not experiencing so much tidal friction. But my whole point, if I hopefully didn't go off the rails with explanation, is that Io really stands out because it's rocky and yet gets tidally heated. But it's in a weird spot. It's like squeezed in there, squeezed in by the big moons that are outside of it and the giant planet it orbits. So differential gravity is kind of the underlying idea here. That's what leads to that tidal friction. So it's that variation in force. So when you consider like the moon's mass, the planet's mass, the distance between them, and the size of the moon, this is like the reason that the sun doesn't drive tides on Earth, but yet the much weaker gravitational pull of the moon does drive tides, because the difference in the gravity is much bigger from the moon than from the sun. And it's the difference that matters for tidal forces. So I'll just quickly go through it, because unless I assign this as homework, you won't be responsible for it. And I don't have a homework planned that uses that equation. So tidal heating of Io, which of the following is not a factor in explaining why Io experiences such substantial tidal heating? I'll give you a chance to answer this, but I won't check the chat because I do want to head to our break in a second. Once we finish with Io. Jupiter is a massive planet. Io's orbit is small. Io's orbit is inclined to the plane of the other Jovians. Io's orbit is elliptical. Well, did you say 3? That's it. It's the one we haven't mentioned, right? Inclination, first of all, it's not inclined. So it's wrong or untrue. And if it was, that wouldn't lead to, substantial tidal heating. In fact, if anything, it would lower the tidal heating. If it was inclined, it wouldn't, be part of that whole resonance cycle. It would still experience, pulls from Jupiter, but it wouldn't experience as dramatic pulls from Europa and Ganymede. So nope. Not only is it untrue, but it would not contribute. All right. So we'll pick up on Callisto after a 5-minute break. Pause. Continuing with our discussion of the moons of Jupiter. We already talked about Io. Let's talk about Callisto. So we're not doing them in order of orbital distance. We're jumping around. And if we go all the way out to the furthest moon from Jupiter, we get Callisto. It's all rock and ice. It has no atmosphere. So like the moon, like our moon. Its density is typical of a rock and ice planet or dwarf planet, really, or moon. And it does have maybe some subsurface water. It's not known for that, but I have heard that before. It's certainly based on some of its behavior. They study the way that worlds rotate. That was actually how scientists first began to suspect that Mercury had a molten mantle, or rather a molten outer core, was because fluids cause a change in the rotation. It's like kind of this measurable difference. And that Callisto seems to be doing that. So is water ice more or less dense than liquid water? Take a minute and think about this, but I won't check chat. Think about, icebergs, ice in a cup, density of water, by the way, 1 gram per cubic centimeter. That's typo. Should say cubic centimeter, not square centimeter. But easy typo to make. Made it myself. But point being is that water ice is less dense than liquid water. That's why it floats. The density is about 0.9. So the density of ice is 90% the density of water. That's why when they talk about icebergs and they say, when you only see 10%, that's about right. 90% of the iceberg is submerged, because that's what happens with floating objects. The proportion that's above the fluid and the proportion that's below is equal to the relative proportions of density. So 90%, 90% underneath. So, and then as a number, it's 0.9. So 0.9 grams per cubic centimeter is the typical density of water ice. So Callisto, slightly larger than Earth's moon, but has much more ice than the moon. So which has a higher density? Well, obviously the moon. Okay, that being dominated by rock, right? Even though the moon is lower density on average than Earth by far, consistent with the hypothesis that it was created from largely our mantle, still that rock is denser than ice. Okay, significantly so. Okay, so now moving right on to Ganymede. Not too much to say about Callisto, as I've mentioned that a few times, right? It is the, I guess you'd say, the least interesting, or at least the least is known about it. Ganymede's main claim to fame is that it's the largest moon in the solar system. It's rock and ice, a little bit denser than Callisto. Doesn't have an atmosphere despite its large size, and that kind of interesting case. There's nothing really maybe that led to a production of a secondary atmosphere, and obviously it lost its primary atmosphere, and it's not unfathomable that with slightly different conditions, it could have an atmosphere. I'm not saying like a breathable atmosphere, because of course that would take, plants in the first place. But it's got a lot going for it in terms of its size, the gravity, even the fact that it's within the magnetosphere of Jupiter, which would help, protect it from some of the really high energy, solar emissions. But despite that, it just ended up not having one. It does have its own magnetosphere, which creates an interesting combination with the magnetosphere of Jupiter. Kind of creates this toroid of magnetic fields, which is like a donut shape. The reason that it's able to have its own magnetosphere is the typical reason when that magnetic field is created internally, it has a warm molten interior. That warm molten interior does not show up as volcanism on the surface because it's not as hot as Io's, but there's leftover heat, and that does sustain a magnetic field. It definitely has subsurface oceans. There's definitely liquid water, pockets of it at least, underneath the surface. There's so much of the upper layers are based on ice that there's big opportunities for that ice to phase change into a liquid and to end up with large oceans, maybe very deep down. Ganymede's surface, looking at some details here in terms of some tectonic activity, stretching going on, creating cliff formations. So what causes the Earth and the Jovian planets to create their own magnetic fields? I'm talking about this a lot, so I'm just going to give you the answer. The movement of materials inside the planets. So it's internally created. It requires molten outer cores in general, at least something molten, but at least all the cases that the Earth, even the very weak one from Mercury, certainly Ganymede, we have a molten outer core. Okay. And that's a key ingredient. It's not the only one. If you remember, rotation is necessary as well. Okay. And going back to our, that variation in force, that contributes to the heat. We're looking at that change in force, and it's not nearly as big as for Io, but it's way bigger than the moon, and that's how Ganymede is able to have a molten core, material that's moving around, and the moon doesn't. See the variation in force that Earth exerts on the moon. No units here, so just worry about the relative values. And this is that same equation that we introduced a few slides back. And also know how big Io's is, which I mentioned a moment ago. It's huge, right? That's why Io is so volcanically active. But Ganymede does stand out being bigger than Europa, even though Europa orbits closer. And that's because part of the calculation here is the size of the moon itself. And Ganymede's large size leads to this greater force variation, thus greater tidal heating. That's what this number kind of tells us, is how much tidal heating is going on. Callisto, very little, right? That was, not quite as small as the moon, but more in that category. If you looked at a section of the different layers of the interior of Ganymede, you would see a saltwater ocean, maybe not quite as uniform as this, but certainly large regions of saltwater ocean underground, underneath a pretty thick crust of ice, described here as hexagonal ice. I don't know much about it, but it's a certain type. Then there is a different type of higher pressure ice that occurs underneath the saltwater ocean, where it's forced to change back into a solid. Ideas that we talked about when we talked about the ice layers on the Jovian planets, right? Like how do you have ice inside, so deep inside of a planet where the conditions are obviously very hot? Well, the pressure dominates. Then the rocky mantle, okay, keeping that density higher than it would be otherwise without rock. Iron and iron sulfide core, that's the liquid part that generates the magnetic field. Maybe the takeaway here is that this is pretty dynamic stuff, right? This is a real, this looks like it could be a planet, There's actually more going on here than Mars. It's smaller than Mars, but still, in terms of it being like an active world with liquid water, well, look no further than Ganymede, even having its own magnetic field. Mars doesn't have that. And so this whole idea that these moons have tidal heating almost like keeps them in this state of being more alive, right? They don't, because at this stage in our solar system, we look at Mars and it's had all this time to cool and just become stagnant and just frozen. But that doesn't happen for these moons. They stay active. And I guess that matters from our human-centric view because, well, they could potentially support life. Maybe they already do, some microbes. Also, they might be good for habitation, future habitation, right? So really like long-term colonization of other worlds really likely will focus on, sure, Mars, right, as a necessary, much closer location. Remember, it's 1.5 AU as compared to 5 to get to Jupiter. So that really matters. Talking a lot of travel time here. But in the long run, if humans survive the next 500 years, I would be surprised, shocked, whatever, that we're not living on these Galilean moons because they just offer a lot of potential. Europa being no exception. In fact, really kind of saving the best for last in terms of the Galilean moons. Okay. I mean, I think that was actually the intention of the slides. So what's going on? What are the key ideas? So it's rock with water ice surface. Okay, so rock core, which we did mention before. Density 3.01. That fairly high, right? High, not one of those 1.7s like we see for the more icy worlds. No atmosphere again, so just total vacuum of space, right down to this surface. The surface is all ice, just big ice sheets. But here's the kicker, is right underneath this moon spanning ice sheet, almost like like the kind of ice sheets we have at our North Pole, right? That float on top of an ocean. Well, these do as well. There's liquid ocean immediately under the surface, and much closer to the surface than with Ganymede. And so there's not, these are like really like just sheets of ice that are moving around on top of an ocean that obviously is warm enough and energetic enough to stimulate the movement of those ice sheets on top of it, which means that there's got to be, like convection and, vents at the bottom of that ocean that are, dry, warming up the water and creating currents. Okay, so here are some surface feature examples. These are all, zoomed in images showing that ice that spans the whole surface. This ice that is a few kilometers thick, floating on a huge ocean underneath. An ocean of water, liquid water. Well, liquid water is redundant, but H2O water, I guess we could say, right? It's not, it's not going to be like a disappointment where you say, oh, well, yeah, it's liquid, but it's all ammonia. No, this is H2O. All these cracks, right? This is showing where the ice sheets have buckled, have cracked, have pulled apart, slid underneath one another. Also some impacts, right? There's cratering, but cratering doesn't last long on this world. There's constant erasure, not from wind, there's no atmosphere, but from this sort of like almost like tectonics, but with ice. So we've got that thin layer of ice and then a thin but very close to the surface ocean that seems to cover most of the planet. So you just cut through the ice and underneath liquid water. So the refacing, this resurfacing, right? Very low cratering, much lower than on Ganymede. And that's kind of the indicator about like I said, the energy of the ocean, the subsurface ocean in Europa, and its proximity to the surface. The fact that it can move around the ice. We don't see that on Ganymede. On Ganymede, there's more water, but it's deeper down. And it doesn't make its way to the surface. And the surface is kind of locked in time and has, billions of years of cratering evidence. Europa doesn't, because it's always losing its craters. They are getting just refrozen as the ice splits apart and the craters get destroyed. Warm spots under the surface, right? That's that energy, the heat of the ocean, have to or have an effect on the planet. It has its own magnetosphere, just like Ganymede. So down somewhere, something going on in this core is generating a magnetic field, a weak one. And there is so this is the ESA launched a mission to Europa, or it's already been launched, JUICE, and then NASA also, just launched in this year, 2025, the Europa Clipper. So there's some real money and interest going to Europa. We have they're not landing missions, but they're close flyby missions to really get some detailed measurements from space. But we can penetrate with radar. We can take samples of gas that's sent up into orbit that came from the basically outgassing from Europa. So it's really actively being studied, and maybe we'll follow up with some sort of landing mission. But it's a popular idea. It shows up in science fiction quite a bit in terms of like a potential first contact with aliens. Maybe there's some squid creatures that live underneath the ice. Moving on to Neptune, because remember we already talked about Uranus. That was our very first coverage of moons, and they were not terribly interesting, but there was a couple of decent sized ones, and with the named after characters from Shakespeare's play. But now we're done with Jupiter, and now we're going to do Neptune. We'll do Saturn last. And with Neptune, our moons of interest are Triton and, just to show you, oh, actually, that's it. Because then the other one is going to be Saturn. Yep. I was going to say Enceladus, but that's not. Wrong planet. So just Triton. So Triton is really the only large moon of Neptune. Remember, Neptune's the furthest planet out. It has a lot of smaller moons. But Triton is noticeably large. It's got some interesting characteristics. So it's got a density that's right on the upper end of a oversized comet, as I jokingly called it. So pretty similar to Pluto, but a little bit denser. It's a lot of ice, right? It's rock, but really has made of a lot of ice. What is kind of a standout feature of it is its orbit. So it's one of those weird orbits. It actually orbits in the retrograde direction, which means it goes clockwise, as seen from above the ecliptic plane. And that means it could not have formed from an accretion disk. Like that, the fact that it's orbiting the wrong way means it had to have been captured. So Neptune captured this essentially dwarf planet. It was probably a Kuiper belt object that through maybe a series of gravitational interactions ended up getting pulled into orbit around Neptune and is in a stable orbit, but in orbiting the wrong way. It has a thin nitrogen atmosphere, which is sustained partially. I don't know if it would be completely retained. It's probably cold enough that retention is possible, but it's at least continually thickened by nitrogen geysers. So there's active geysers, ice geysers, ice volcanoes sometimes called. No tidal heating. Neptune's quite a bit smaller, and Triton doesn't orbit very close, which is typical of captured bodies. Captured bodies don't tend to be the close orbits. Because that's where the capture can happen stably. If you think about early solar system, all the captures that didn't work out ended up being collisions, right? And so the later stable captures happen at greater distances. Also, the accretion disk is what explains the close-in moons, like the 4 that we just talked about for Jupiter. And accretion disks don't extend that far out because the matter gets too thinly distributed. Going back to the nitrogen geysers on Triton, we can see evidence of them here. I'm not sure where to look because I see some craters, but you can look into that if you're interested, but you just need to know that they happen. Oh, there they go. Forgot those arrows. Yeah, oh, yeah, cool. Yeah, it's so obvious. Yep. These big dark spots. Neat. So it has a eccentricity. So the eccentricity of Triton's orbit is 0.0000016. So that means it's very, 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 give you a chance to answer yourself. If you want to think about it, you remember what that means? It means circular. It's almost a perfect circle. Without an eccentric orbit, the tidal forces of the moon don't change. So even if it was close enough to get some decent force, there's no variation. Okay, so there's no flexing. All right. There's sublimation occurring with solid turning into a gas. The sunlight is causing a phase change that skips over the liquid phase. So the surface sublimates. This happens on Pluto as well. Pluto, because of its elliptical orbit around the sun, when it's at perihelion, there's obviously significant sublimation that creates a sort of a temporary atmosphere, and then the atmosphere freezes out as Pluto approaches aphelion. So the air pressure is too low to squeeze the atoms into a liquid. That's why they skip over that phase entirely. Sublimation can happen on Earth as well under certain conditions, up at like the poles, where there's just like so much energy coming in at once from a combination of wind and direct sunlight. And so like the ice sheets of the poles can like just sublimate straight into a gas. So does dry ice, by the way, obviously. It is famous for going straight from solid to gas. All right. And so, typically water, requires an air pressure of at least 1/165th of Earth's atmosphere, except when it doesn't, And nitrogen needs just a low pressure of 1/8 Earth's atmosphere, which is why it's pretty easy for sublimation to happen on Triton. It easily meets the standard for having easy nitrogen sublimation because it has an atmosphere with a pressure that's 1/70,000th. So it's a very thin atmosphere. All right, so finally on to Saturn. Okay, so the moons that we want to talk about, the icy moons of Saturn, Mimas, Enceladus, Tethys, Dione, Rhea, and Iapetus. There they are. All right. There's so that one is Iapetus that I just pointed to. That arrow. Okay. And then the really big one here in the background is well, it's not mentioned yet, but it will be. So see how this is huge moon, and it's like looming in the background. All right. And I mentioned this last arrow, so I'll do it because it's kind of hard to tell where it's coming from, but that's Iapetus. Iapetus has this characteristic equatorial ridge. Really kind of a strange feature. Now the one that isn't mentioned, the one that's not a icy moon, but kind of is, if you talk about its interior, its composition, we can tell right away because of its density being fairly low. So its interior is made out of rock and ice. But its claim to fame is not that at all, but the fact that it has a thick atmosphere. It is the only other thick atmosphere in the solar system other than Venus and Earth. And of course, Venus's atmosphere is a mess, right? It's just so thick that it creates these incredibly hostile conditions that just don't really lead to much going on. I mean, not even very much interesting chemistry, let alone like any survivability for life. But Titan is different. Titan has a very cold atmosphere, so it's not like it's not going to keep you toasty, but it's also not totally hostile to at least maybe some potential life. I mean, people actually study like that. Could there be like very different life that lives on Titan that isn't water based? Is it possible that there is methane based life, right? Using methane in the same way that life on Earth uses water as this kind of key mechanism to move molecules around. And the reason is because the thick atmosphere contributes to a cycle, a precipitation cycle that includes lakes, rivers, seas, rain of methane and ethane. So there's actual precipitation, clouds, watersheds, but they're not watersheds, they're liquid methane and ethane. And okay, that's interesting. Why methane and ethane? Because of the low temperature. So the surface temperature of this ocean, or rather the surface of this moon, and it does have small oceans, lakes, really not oceans, but lakes. It's sufficiently cold for methane and ethane to be liquids, right? Whereas they would be a gas, typically on Earth. And so the atmosphere, like any atmosphere, has a greenhouse effect. But here, greenhouse effects can only do so much. And so, yes, it creates a warmer Titan than if Titan had no atmosphere at all, but it's still cold by, kind of human standards. Okay, definitely has underground oceans. I don't know much about them. I don't think they're water, but maybe they are. They could be liquid methane and ethane. I'd have to look into it. We have an infrared light image because that pierces the atmosphere. visible light doesn't. So this is using infrared to pierce the cloud layer and see the surface and see the lakes of methane. So the planet Mercury has effectively no atmosphere, while Saturn's moon Titan has a very thick atmosphere of hydrogen, argon, methane, and ethane. How can this be the case? Well, because of the distance from the sun. Okay, it's just because this is a cold world. Titan is, it's far out. Sure, it's only Saturn, right? So it's not as far out as, Uranus and Neptune, but the sunlight is not nearly as intense as it is in Mercury. We're talking a huge difference. And that's how something like this can occur. But it's also not a sure thing, right? Like I pointed out, Ganymede, under just slightly different outgassing conditions, could have developed a secondary atmosphere that lasted. For some reason, Titan did. And the exact mechanisms aren't clear, but they both had the potential, but Titan does have an atmosphere. A little bit more about it. The thick photochemical haze obscures the surface, all right, which is partially covered in liquid, ethane and methane. So in visible light, it actually looks a lot like Venus because it's just opaque to visible light and kind of reflects in this yellowish color. And the atmosphere itself is actually kind of cool. It's got a bunch of nitrogen, like our own atmosphere, right? But we've learned that nitrogen is a common component of the outgassing secondary atmosphere of planetary formation, applies to a lot of these moons as well. And so presumably the nitrogen was outgassed and stuck around. Whatever primary atmosphere, hydrogen and helium was lost. All right. And then the only 2% of the atmosphere is composed of methane and other hydrocarbons. But that makes sense. I mean, think about our atmosphere. We have a water cycle with clouds that rain water, but water makes up a tiny portion of our atmosphere, much less than 2% for that matter. So the fact that the value of methane in the atmosphere is low, doesn't, preclude the existence of, methane rain. And there's, although we haven't literally filmed it raining, there's very good evidence that is what's going on. All right, here is a map of the surface of Titan. There's a maze of valleys made by erosion because since there's a full precipitation cycle, right? I always want to call it a water cycle, but let's call it a liquid cycle, right? Evaporation, clouds build, precipitation follows. That means that there's erosion. So there'd be very little cratering because everything gets eroded away. There's rough, uneven, icy terrain, hummocky, right? A term that gets used for terrain here on Earth as well. All right. So maze of valleys made by erosion. Be probably horrendous to navigate if you're driving around with a rover or if you send a robotic rover there. Cold temperatures and high pressure at the surface support liquid ethane and methane. It's not high like Venus high at all. It's not even as high as Earth, but it is notably high because we talk about atmosphere sometimes. We talk about wind on Mars requires an atmosphere. We're just talking about the thin atmosphere of Triton, and there's 70,000 times less pressure than Earth. Well, that's not the case of Titan. I don't know. I don't think they have the value here, and I don't remember what it is. But it's much closer to Earth atmospheric pressure, although less. So I don't know. It's such an interesting fact, right? That it's really kind of almost it's the most Earth. Actually, this is the way I've heard it described. I think this is a good way to stick it in your mind. It's the most Earth-like atmosphere, and not that it's that Earth-like, but still, that's nothing else comes close. It's the most Earth-like atmosphere in the solar system, in terms of its pressure, anything. So you could go to this planet, you couldn't breathe because there's no oxygen in the air, but the nitrogen is harmless. And so you wouldn't have to worry about some of the effects of like vacuum, although it'd be really cold. So it would actually allow for certain like ease in spacesuits. You wouldn't need the same kind of the same type of vacuum protecting spacesuits that you even would need on the surface of Mars. Certainly on the surface of the moon. So there's some real advantages of walking around on Titan. Just don't get lost in the labyrinths of valleys. All right, the seas are named for mythological sea creatures, sticking with the theme of the naming. where in contrast to a Venus, where all the surface features are named after mythological women, just so you know. Okay. And then in terms of, this is just a cool summary about tidal forces, since we've been seeing a lot of them. Titan does have them, by the way. Remember, Triton didn't. Titan does, both because it's close to Saturn and because it has a somewhat elliptical orbit. And so I love it. They have this, and we haven't mentioned it yet, but I'm going to point it out now. Tidal locking, that's like what, our own moon. Okay, so Earth's moon, right? They have one face point. Tidal locking is almost universal with the large moons. Every large moon in the solar system is tidally locked to the body that it orbits. Look, Callisto, maybe Titania, Ganymede, Io, Triton, Europa, Titan, Enceladus, which we'll talk about in just a second, Earth's moon, every large moon in the solar system. So like that, it's just like, that seems to be what happens with large moons orbiting a planet. They get tidally locked. All right. So a planned mission to Titan coming up. All right. So, this is the one that happened. Yeah. So this didn't go so well. They almost totally failed, but they managed to actually land it, although at a much greater velocity than they had planned. And they got 70 minutes of communication. So they got a few images, but they'd planned on weeks. There wasn't a rover, it was just a lander, but it was going to collect images and take readings with certain sensors. But they barely got it to work at all because it hit the ground way faster than they had planned. There's actually a crucial miscalculation which was caught in like the last couple days of approach. So, this gives you the idea that it's a long distance mission. And so the fact that they made a mistake and didn't catch the calculation to the last minute is a real shame, because it's like sending a virus from a basketball to a baseball with the distance between the two of being 15 miles, right? So it's like that's a long trip for our little virus, being our space probe. It wasn't mentioned, but there is also a approved, although not launched yet, but seems to be fully funded future mission planned to Titan. That's going to have a lander and a helicopter. This like a little tiny helicopter, sort of based off the successful design of the helicopter that was used on Mars, which really proved very effective and is much better suited to the thicker atmosphere of Titan, and would be great for flying over the terrain, which is almost impossible to navigate by rover because it's so hilly. All right, so other interesting moon, and actually one that is of really great interest, potentially the best candidate for life in the solar system, outside of Earth. There's life here. Enceladus. Okay, it's another moon of Saturn. Shown below, it's a lot like Europa. It's like a smaller version of Europa. All right. So, and you can see, right? So if you look at it, right, you can see this, these big ice sheets. We have, big valleys, very little cratering. What does that tell us, right? It tells us that it is tectonically active, but not with rock, but with ice. Okay. It has a low density because it's mostly just liquid water and ice. It has a thin water vapor atmosphere because there is regular outgassing. There are geysers. So Europa, sure, there's movement, right? But Enceladus, the ocean underneath is warm enough to actually regularly crack through the ice and shoot geysers. And because the gravity is so low, because it's actually a rather small moon, the geysers actually like shoot, incredible distances relative to the radius of the planet, and actually, send water droplets into orbit. So, this like space geysers in a sense, but again, context of such a small world. But that means that the ocean has to be heated, right? There has to be probably volcanic vents at the bottom of this ocean covered by a thin sheet of ice. So subsurface ocean with geysers that spray water into space. Look at this image. So the actual image taken from the Cassini mission that went to Saturn. They hadn't even really planned on studying Enceladus. It goes to show it's recently of scientific interest. But then they started to realize that, oh wow, and then when they realized that it has these geysers, they changed some of their trajectory and did a couple of flybys. Okay, so this is showing that the ice sheet that covers the subsurface ocean, liquid water, and then how's the water able to be so active? Probably because there's volcanic vents, like there's volcanic vents at the bottom of our oceans. And what do we find at volcanic vents at the bottom of, say, the Atlantic Ocean? We find life forms that have evolved on those vents, completely independent of the ecosystem that relies on sunlight. There are crabs and shrimp, and it's also entirely possible that that's where life started on Earth, on the subsurface vents, and not on a surface primordial sludge case. Both kind of primordial sludgy, but one would be at the bottom of the ocean. So maybe there's life on Enceladus. Right, here's the Cassini view of it. Yeah, because this one, oh, okay, this one is just a representation. This was not the actual photo. This one's the actual photo. Look at those geysers. Right, they produce a donut-shaped ring, right, going out into Saturn's atmosphere because of all the gas that gets left in space. So geysers create Saturn's E ring. Right, there we see Enceladus relative to the rings. Pretty cool photo. All right, about the rings, and wrap things up. This is kind of like the question that you saw, kind of out of order. All the Jovian planets have rings, okay, but only one of them is bright. The other ones are very faint. Really, you have to see them in infrared. Okay, Saturn's rings do have a lot going on. They have these complicated sort of system of rings. The thing that I want you to know the most is that it's first thought to be a triple star. Makes sense, right? When you look at it with like a really basic telescope, it looks like it has little ears, like that. That's what I've seen through kind of like hobby telescopes. It looks like a bright circle with two little like ears on it. All right, so later on, right, history of discovery of the rings. They're not a solid piece. It's not like just a big sheet. It's just tiny little particles. Also, some pretty big chunks. So the chunks range from centimeters to meters. There's also within the rings. So this is kind of what they look like. The composition of them, full of rocks and ice. Within the rings you have moons. So there are moons that orbit no large moons. Large moons are always outside of the rings, like we saw in the quiz. But there are these small moons, sometimes called shepherd moons. I'm skipping through some of this. So if we look, we have these gaps, and there are moons that actually exist in the gap. And we call them shepherd moons because of their gravitational interaction, they've cleared that band and created the very gap that is their orbit. So they shepherded the dust out of the way. The ring structure is very flat, like orbital structures tend to be, especially ones that are associated with accretion. All right, and why are there gaps? And so sometimes because of resonance, and also because of the moons, combination of them. So the resonance would happen with more distant moons. All right, so a moon and the rock are close together in space. What is the direction of the gravitational force that pulls them together? There's a lot of slides here, so I'm just going to need to go through the rest of them. All right, so moons can cause ring gaps by clearing out, as I talked about. All right, so they're pulling the mass. Where did the rings come from? Since these rings probably just last for a few thousand years, maybe a few 100,000, probably from a small object getting torn apart due to tidal forces. That's there's a small moon that got torn apart and made the rings we see today. This idea of a moon or other body getting torn apart by a planet actually is associated with a known calculation and named after the scientists associated with that calculation, and the limit called the Roche limit, and is the closest distance to a body where large objects can orbit, because if they go closer, they get pulled apart due to tidal forces. So here's the calculation. This is the minimum distance for a rocky body, because different substances have different stress levels they can handle. And it's 1.2 times the size of the main body, and then multiplied by the fraction of their densities raised to the 1/3 power. For icy bodies, you can get your minimum distance is greater because you can't get as close because ice is more easily torn apart. That's why it's 2.4 instead of 1.2. So are you more likely to find rocky or icy moons close? Rock, okay? Because the icy moons wouldn't last. They just contribute to the rings. All right, so this is showing the moon getting pulled in. So you have some sort of elliptical orbit, maybe because of a perturbation, and then it gets torn apart and then becomes the ring. And then on the rocky Roche limit, we have a similar trajectory and something getting torn apart. Maybe it's not even a moon that got disturbed, but a comet, right? So a comet comes from the outer solar system, moves in, gets torn apart. In fact, speaking of comets, in 1994, the Shoemaker-Levy 9 comet, they're always named after the people who discover them, hence the names that sound like, people's last names. They are. Passed close enough to Jupiter to enter its Roche limit and got torn apart, and then then landed as a series of pieces, right? So it got ripped apart through the tidal forces, and then just continued in a trajectory, and then landed like that's the best way to describe it. Okay, let's see. Let's jump over to scanning through them. Definition of a planet we'll skip over, and we already really talked about Pluto. So I'm going to wrap it up right here. See the time? Yeah, perfect. So we can at least get done with this lecture. So everything we talked about is, I think we covered all the key things that that you'd see on a quiz that's relevant to a homework or discussion question. We got through it. All right, so now stop the recording.